before the sun had fully crept over the horizon. Subtle hints of something unusual were already unfolding along the California coast. Dock workers, familiar with the daily rhythm of tides and shifting lines, noticed mooring ropes pulled tight in strange directions. The tension wasn't violent, but it was undeniably out of place. Farther inland, early hikers moving through the coastal foothills felt the ground behave in a way that didn't match memory. The earth beneath them carried a faint sense of unfamiliar rigidity, as though the topography had adjusted ever so slightly while they slept. Most people brushed off the oddities. Instruments malfunction. Early morning fog distorts perception. Sleepy minds sometimes misinterpret the world around them. But inside the digital nerve center of the United States Geological Survey, a much more disturbing picture began linking together. What the public dismissed as quirks appeared in scientific terms as a major geological deviation, one impossible to misread or ignore. Before we dive in, make sure to like this video and subscribe for more updates, because what happened next left even veteran scientists stunned. Tectonic monitoring stations lying along the Pacific Plate boundary began transmitting data even before dawn. Their numbers showed a rapid, coordinated upward movement along multiple segments of the continental margin. At first, analysts suspected noise, faulty readings, miscalibrated sensors, software issues. But then, seafloor pressure gauges located miles offshore chimed in with equally troubling data. These instruments are designed to detect the slightest changes in water column weight, and they, too, registered synchronized anomalies. This was no equipment glitch. The signals weren't scattered or contradictory. They were unified. They told one story. Something massive had pushed upward. A stretch of California's coastline, extending for hundreds of miles, had risen. Within minutes, the pattern had rippled through every major monitoring system. Ultra-precise GPS stations that normally record crustal flexing down to millimeters all reported the same trend. Elevations had increased since the previous tide cycle. The numbers painted a picture of abrupt uplift, the kind that alters landscapes without leaving obvious visual scars. And when the implications settled in, the USGS issued a message they hoped would never be necessary. Red alert. Significant tectonic uplift detected along the California coastline. The notification spread with the urgency reserved only for most extraordinary geological events. Researchers would spend decades studying the slow, almost meditative evolution of fault systems suddenly face a phenomenon that seemed to skip all known steps. This uplift wasn't gradual, wasn't expected, and defied many established models. It happened in a matter of hours. A sudden vertical shift of land means enormous forces are at play beneath the surface. Forces usually quiet for centuries before releasing their power. Such an event hinted that pressure was reorganizing throughout the region's tectonic architecture. For a state built on one of the world's most watched fault networks, this was nothing short of baffling. Seismologists traded rapid-fire messages, hoping someone had discovered contradictory readings. But every dataset confirmed the anomaly. Geophysicists annotated the uplift pattern, trying to determine which structures had shifted. Marine geologists rushed to analyze offshore data to learn whether the ocean floor had risen uniformly or in distinct blocks. Strangely, the measured uplift, though small in height, was immense in scale and precision. To ordinary residents, the effects were nearly invisible. Beaches didn't suddenly extend outward, cliffs didn't rocket upward, and no roads warped overnight. Yet subtle hints appeared for those who paid attention. Tide pools sat a bit higher on the shoreline. Boat channels seemed marginally tighter. A few piers tilted just slightly more than the day before. These little details told scientists everything they needed to know. The coastline had moved. What truly unsettled researchers was the silence accompanying the event. Typically, rapid vertical displacement comes with seismic signatures, foreshocks, rumbles, tremors. But this uplift arrived with barely a whisper. It was as though the earth had rearranged itself smoothly, bypassing the violent friction normally associated with tectonic adjustments. California's coast sits atop a complex boundary where the Pacific Plate grinds relentlessly against the North American Plate. Most people hear about the horizontal movement, the legendary San Andreas Fault. But beneath that well-known system lies a labyrinth of lesser-known secondary faults. blind thrust faults, and offshore segments capable of interacting in unpredictable ways. This uplift suggested something deeper was at play. Some scientists theorized that pressure had been building far below the crust, perhaps within the upper mantle. Others wondered if previously dormant faults had shifted. Historical records provided almost no comparisons. The event was unnervingly rare. The uplift wasn't random. It followed a smooth, sweeping curve that matched the shape of the coastline. It was as if a giant invisible hand had nudged the edge of California upward. For the crust, which is stiff, brittle, and prone to breaking, to move this cleanly implied an enormous, unified force. Speculation erupted. A deep-seated fault realignment? A vertical shift in a previously unmapped tectonic block? A pressure redistribution spanning hundreds of miles? Nobody had clear answers, but everyone agreed on one thing. The uplift was geologically extraordinary. Beyond the scientific implications, the real-world consequences loomed. Even a slight elevation change alters tidal dynamics. Storm surge behavior, groundwater flow, and coastal erosion. Over time, cliffs might destabilize, landslide-prone zones could shift, and low-lying communities might see tidal ranges behave differently. Infrastructure planners, city officials, and engineers quickly recognized the stakes. Bridges, harbors, and pipelines near the coast rely on stable baselines. Even a few centimeters of vertical motion can impact design assumptions that have been in place for decades. The uplift also forced a reevaluation of tectonic models. For years, scientists believed they had a decent grasp of how stress accumulated in the region. This event disrupted that confidence. If uplift could occur without a major earthquake, then the internal mechanics of California's crust might be even more intricate than previously known. Offshore fault systems, in particular, demanded renewed scrutiny. Much of California's tectonic activity happens underwater, where data is harder to collect. If a major offshore segment had shifted, smoothly and silently, it could reorganize stresses inland. Coastal ecosystems were also affected. Many species depend on narrow tidal ranges for survival. Even slight shifts could alter habitats for mollusks, seabirds, kelp forests, and intertidal organisms. Biology responds to the land's elevation just as surely as geology does. Meanwhile, researchers investigated deeper processes. One compelling hypothesis proposed that the Pacific Plate experienced a slow slip event, extremely subtle, long-duration movement that rarely produces shaking but can shift vast sections of crust. If this slow motion happened faster or more coherently than usual, it could explain the uplift. Another possibility centered on ductile behavior deep beneath the brittle crust. At certain depths, rock becomes plastic and can deform smoothly. If such material bulges upward, it might lift the surface quietly without generating earthquakes. Some even examined fluid movement deep underground. Pressurized water or brines could force straight apart, lubricating faults and allowing upward adjustment. In the meantime, satellites monitored elevation changes. GPS data poured in. Offshore buoys watched for further anomalies. Researchers compared new measurements with seafloor maps from previous expeditions. Every source confirmed the same story. The uplift was real, widespread, and coherent. Research vessels diverted course to collect seafloor scans. When sonar imaging revealed that ridges and troughs beneath the ocean had shifted too, it became clear that the uplift was not a localized surface event, but part of a much broader tectonic rearrangement. What startled many scientists was how clean the deformation appeared. Sediments were not violently torn but lifted almost intact, suggesting a smooth rise rather than a rupturing break. Ocean currents even showed subtle directional changes, influenced by the seafloor's new shape. Over time, such changes could alter nutrient flow, impacting marine ecosystems. As international experts joined the investigation, new theories emerged. Some suggested mantle convection patterns, slow-moving currents deep beneath the Earth, had reached a tipping point, pushing the region upward. Others speculated that distant tectonic disturbances, possibly across the Pacific, had sent stress waves that redistributed pressure along the California margin. Survey teams revisited decades-old benchmarks across the state, comparing their precise elevations. Some sites had risen mere millimeters, others several centimeters. Hydrologists examined how groundwater levels responded. discovering slight rises and dips depending on local pressures. Engineers assess harbors, tide inlets, and bridges for any signs of stress. Satellite radar interferometry delivered the clearest image yet, a gorgeous, colorful elevation map, revealing a smooth, curved uplift pattern. Its symmetry mirrored deep tectonic structures long theorized but never observed. Some geologists began to wonder whether California was experiencing a rare tectonic breathing cycle, a slow and steady release of stress through periodic vertical adjustment rather than violent rupture. Even atmospheric scientists entered the discussion. Although uplift is small, wouldn't directly change climate. It could affect microclimates, fog paths, sea breezes, temperature gradients. Residents along the coast started noticing changes too. Sea caves looked slightly reshaped. Shadows fell differently along rock shelves. Photographers who returned to the same vantage points noticed angles that didn't match older pictures. Meanwhile, experts in coastal law raised a surprisingly practical issue. Elevation determines legal boundaries. When the land rises, so does the mean high tide line. Even if the uplift was subtle, it raised long-term questions about how such changes should be managed legally. Specialists studying Earth's magnetic field detected slight variations in magnetic signatures along the uplifted zones, suggesting deep rock layers had shifted orientation. Sedimentologists observed minor shifts in sandbar behavior, while marine biologists documented kelp forests redistributing themselves as anchor points rose into brighter water. Even marine mammals changed their movement patterns, guided instinctively by altered underwater topography. In the end, one truth became clear. The uplift was not catastrophic, but it was profoundly important. It was a reminder that Earth remains an active, evolving planet whose movements we cannot always predict. Even in one of the most heavily instrumented geological regions in the world, the crust retains the ability to surprise. The California coastline had moved, not violently, but decisively, and though scientists will spend years untangling the full meaning of the event, one fact already stands out. The Earth quietly rewrote the rules. And now, researchers must rewrite their models to match. If you enjoyed this video, remember to like and subscribe. And let us know in the comments, what do you think caused the USGS red alert after California's coastline rose? Thanks for watching, and we'll see you next time.